Okay, so as I promised last week, dead week this week, no homework, no quiz. Wait, no, the homework is, there's still a homework problem that's due on Wednesday, right? But I'm not adding any homework. There will be no quiz. I've given you I believe it's a 12-page, not final review packet, right? Okay, apparently I made a big deal of that and then I put it in here. I mean, this is just like course summation packet. Again, what I'm trying to communicate is do not rely solely on whatever is in this packet being the only thing that's on the final exam, right? But these should help you with the final exam. I don't know. I just don't come to me afterwards and be like, hey, there weren't any problems in the final packet about blah, 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 blah. Okay? All right. So, should we start at the beginning?
Sure.
I figure.
That'd be a good place to start.
Yeah. Okay, so we're going to start at the beginning with force summations, right? Way back. Probably knock these out pretty quickly. Couple ways to do these, right? So determine the magnitude and direction of the resultant force, Fr, measured counterclockwise from the positive x-axis. Solve the problem by first finding the resultant F prime of F1 and 2, that's these two, and then form the force resultant by adding F prime to F3. Okay? And we can see that we are 150 degrees here, 90 degrees there. Well, those are funky because we don't really know where we're at from x and stuff, right? We can solve for it? How might we do that?
Because 150, F3 is 90 degrees off the x-axis, so what's remaining?
F3 is 90 degrees.
So
Look at that. Sierra very astutely pointed out, look, F3's on the y-axis, so we know that's 90 degrees. So this is going to be 60, right? Now, I wasn't being facetious. I didn't see that until you said that.
Yeah, that's so smart.
Okay. How I was going to solve it, because I didn't see that, is I was going to say, okay, let's combine F1 and F2, and we can do that by moving F2 tip to tail, right? So here's my 200. And we know that it's perpendicular because we're told that it's 90 degrees off. So my resultant, so this is F2, my resultant would be right here, which they called F prime, right? And I could find the magnitude of F prime if I wanted to, if we're going to go old school with this, and do 400 squared plus 200 squared square rooted. Does anybody know what that would be?
447.
447, okay? And if I wanted to find this angle here, I could do that by taking the inverse tan, right, of the rise, 200, over the run, 400, or the inverse tan of a half.
Oh, sorry. 26.6.
26.6 degrees, okay? So if this is 26.6, that would make this angle, what was that, 63.4? Sierra, could you hand this to Brendan to hand to Preston? Okay. I mean, can you guys see how we could keep doing this way? Is this painful for anyone else? It's painful for me.
Yeah.
How would you guys do this problem now that we're not in chapter 2? Yeah, break it into x and y components and just do it all at once, right? So the way that we would do this now that we're not learning how to do it is we just say the resultant in the x direction, let's say, is going to be 400. That's 90, that's 60, so that'd be 150, right? 90 plus 60 is 150, so that means this is 30 degrees. So it'd be 400, negative 400 cosine 30 plus 200 cosine 60, and no F3 component, right? And then the force resultant in the y, we would say would be 400 sine 30 plus 200 sine 60 minus 300 equals 0. Not, oh my goodness. It jumped forward like a million chapters. Okay? What did we get?
You have 246.4.
In the x?
Yes.
Negative 246 newtons. And in the y?
73.2.
73.2 newtons. So our resultant looks like would be someplace about there, maybe? Approximately? You guys remember how to do this? Okay. So 2 dimensions is pretty straightforward. I threw in one of these 3-dimension ones because it's been a long time since we've done coordinate direction angles.
Yeah.
Right?
I don't miss
Guys remember these?
Yeah.
Okay. What's the trick to coordinate direction angles, Brendan?
Knowing if it's azimuth or straight off the axis.
Yeah, so F2 we would call, it's transverse azimuth, is that right? Or azimuth transverse, I think is what they call it. Where azimuth is the angle off of the XY plane. So in this case, we have that based on a 3, 4, 5 triangle. And then the transverse is the 20 degrees off of the X. So we first, to figure out the components of F2, we would first translate it into 2 vectors. One that we would call F prime that lies in the XY axis, and the other that lies purely along the Z axis, and we'd have F2Z here, right? So this is azimuth transverse. But then what's the, you remember what the equation is for when you have coordinate direction angles? Yeah. It's the cosine of what? Yeah. So if I want to find the component of F1 sub x, it's going to be F1 times the cosine of alpha, right? Which is the coordinate direction angle from the x-axis. So in this case, that would be 400 cosine 45 degrees, right? And F1y would be 400 cosine 60 degrees. And F1z would be negative 400 cosine 60. Right? What'd you find?
283.
Yeah. Or 282.8.
For F1X?
Yeah.
Okay.
So I tried to start at the top. So
283, and the Y?
200 and negative 200.
200 and negative 200. Okay. And now what about this other guy? How are we going to do that?
Well, there's a 3 4 5 triangle. Can you use that?
Absolutely. There's a 3, 4, 5 triangle, so we can use that. F2Z would be 3/5 times 125, which looks like it's going to be 75, I think. Okay. F2 prime would be 4/5 times 125, which is 100. Now, does 100 come into our problem anywhere? Yeah? Is that one of the answers?
No.
No.
But we use it.
But we use it, right? It's just this temporary in-between vector. So if we wanted F2x, it would just be the magnitude of our temporary vector F2 prime times the cosine of 20. And F2y would be 100 times the sine of 20.
So this is 100. You can do this one. Put it down there. So this was the 75 and the 100. You drew this one. Gotcha. And so you have this 20 degree angle. This is your x, y. Okay. So x y.
94.0 and 34.0.
Okay?
Is that a 94?
That is a 94. Yep. So then my F resultant would be 283 in the x there plus 94. Oh my, 377? Is that right?
Yep.
I hat in the y, it's going to be 234.2. I can do that one. It's 234. Okay. And in the k hat, we'll have negative 200 plus 75 would be negative 125 k hat, and that'd be newtons. Okay, so where's our resultant end up? Well, quite a bit in the x, a decent amount in the j, and negative 125. So, oh gosh, I'd say it's like right here. I don't know. Maybe it's over here. Okay. Remember the two types of three-dimensional vectors? Everybody good with these? Could you find their components if you needed to? Both types? Right? Azimuth transverse and coordinate direction angles are the two types. Okay? Make sure you can do that. Not because it's likely that you'll have a problem that is as simple as this, although if you do, you want to be able to get that money in the bank, right? But it's likely that you'll have a problem more complicated that will have a three-dimensional vector in it, and so you need to know the two different ways that it could be defined and how to break it into its components, right? Because we didn't spend all term just doing this, right? Okay. So let's flip actually a little bit deeper into the packet. I didn't do them necessarily in order. I recycled some from years past and I added some new ones. Christmas present. So let's go to
Or Hanukkah.
Keep going.
The Hanukkah starts today.
you know,
No, it started yesterday.
the Dickens story is actually Christmas past, isn't it? Or it's in what is that? Is that a Christmas story by Dickens?
The Hanukkah starts today.
Yeah.
Oh, it does?
All right. Ready? So chapter 3 is about things being in static equilibrium. Okay? Two-dimensional static equilibrium. We have some springs here, right? Determine the unstretched length of spring AC. That's this guy. If a force P of 80 pounds, right here, causes the angle theta equals 60 for equilibrium. If chord AB is 2 feet long, we know this is 2 feet. Okay. Take K equals 50 pound. Causes the angle theta. This is 60. Sorry. Take K equals 50 pound per feet. Okay. Kind of a confusing problem. How do you think we should start this? Mr. Mick has been paying attention. Speak up, Mr. Mick. Un cuerpo libre. Free body diagram, okay? What do we know in our free body diagram? Okay, so we know that there's a force down here. This is straight down, even though it doesn't look quite like it. And the force straight down has a magnitude of 80 pounds. What else do we know? We know the distance between B and C, but we're drawing a free body diagram of what point? Yeah. Natasha's got it. She says we're going to draw the free body diagram at A. There's going to be some force here that I'll call TAC. And there's going to be some force here that is TAB. All right? Now, right now, we have quite a few unknowns, right? Because vectors have magnitude and direction. And in 2 dimensions, how many equations can we, in 2 dimensions, looking at a particle, how many equations of equilibrium can I write?
2.
Just 2, right? And right now I have 4 unknowns, right? Because I have the magnitude of AB, the magnitude of AC, and their directions. Until I notice, hey, this says it's 60 degrees. So that means this is 60 degrees, right? We're down to 3 unknowns. Okay? What else can we figure out? Yeah, Michael's exactly right. We can figure out the direction of AC. Okay? So we know that this is 2, this is 4, and this is 60. So I think is it the sine law? Or the cosine? No, it's the cosine law that we're going to want to use here, right? Isn't, what's the law of cosines? Isn't it something like a squared plus b squared, is it minus 2ab or plus 2ab? Yeah, minus 2ab cosine little c. Is that it?
Yep.
Okay. So this would be my a, this would be my b, this would be my c. So we'll have 2 squared plus b was 4 squared minus 2 times 4 times the cosine of 60, quantity square rooted, should give me c, right?
How do you know it's cosine of 60?
How do I know that it's cosine of 60? Well, because the way the cosine rule is set up, you end up, the big capital A, B, and C are the 3 sides of a triangle.
Right.
And then the little c is the opposite, or the little value is the opposite. So this is little c, this is little a, this is little b.
Gotcha.
Right?
3.46.
So we find that c is 3.46. If you didn't remember this rule, how else could you have done this with some trig?
You
Yeah. Right? You could split it into two triangles. And then you could say that 2 sine 60 would give you this height. What would 2 sine 60 be?
Root 3. 1.73.
So this would be 1.7. And that means 2 cosine 60, is that a half?
Yes.
Okay. So that means that this distance then,
I'm sorry, it's 1. Half.
yeah, cosine 60 is 1, so this would be 1, or is half, so this would be 1. Okay. So that means that this is 3. So then I could figure out that 3 squared plus 1.7 squared would also give me C is 3.46, I hope. Okay. Does that make sense? Now, why does that help us? Because now I can figure out what this angle is, because it's going to be the same as this angle, which I could either, I'm going to do the inverse tan of the rise, 1.7, over the run, 3.
Uh, 29.5.
29.5 degrees. Okay. So that's going to go right here. Okay. Is it solvable now? Okay. Go ahead and write the equations of equilibrium for this. Hopefully you got some equations that look like this. Okay. So when you solve, what do you find for TAC and TAB?
C is 40 meters. TAB is 69.7.
Okay. I think we got pounds. TAB is what? 69.7?
Yeah.
Anybody else concur? Great. Okay. Is this what the problem was asking? No. Okay, so it says chord AB, determine the unstretched length of spring AC if a force P equals 80 pounds causes it to be in equilibrium in this position. So we know that K is 50 pounds per foot. Okay, so TAC needs to be a force of 40 pounds. Okay, so then the force of a spring is K times S, which in this case is 50 pounds per foot times the distance it's stretched, X, and that has to be equal to TAB, which is 40 pounds, right? So we have to solve for X. Looks like X is, what, is that 0.8?
1.25.
1.25. No. I think it's 0.8.
Sure.
Right?
Yeah.
0.8 not pounds. Whew! Watch my units there. Geez, Andy. 0.8 feet. Okay? That's the stretch, that's the amount of stretch we have. Right? To get that force. So we were asked to find the unstretched length. All right? So really, we could have I suppose we could have written it differently. I could have said that the force of the spring is equal to K times S, which is equal to 50 pounds per foot, times its current length, which we determined to be 3.46, minus its unstretched length, has to equal 40 pounds, right? This is kind of the same thing, but rather than this is finding the delta, the change in the length, and this is just substituting that in. And this, I will say, is the change in length. Substituting that in and then solving for x, we should find that x in this case is 2.66 feet. Is that right?
So let's say when the spring is like resting, it's at 2.66 feet.
Yep, that's exactly
So that
right.
makes that picture up top
Goofy.
like a lie.
Goofy, yeah. The picture is, well, so the picture doesn't tell us that this spring was ever necessarily here. It's just telling us the length of this cord was 2, right? And so Brendan is correct in pointing out that, well, the spring would never be here unless it was compressed, because we found an unstretched length of 2.66 feet.
And they're calling the bars at the end of the spring part of the spring itself?
Yes, they're calling the bars at the end of, whenever you have a spring in this class, you can consider its length as being from connection point to connection point.
Okay.
Yep, so it includes the bars. Okay, any questions on this? As I recall, I think I've used this problem before, either on a midterm or a final. I can't remember which, but I give it to you as a quiz?
I think it's a similar one.
A similar one, okay.
I looked at the results.
Yeah, I know it's familiar to me. Okay, so this is equilibrium, 2 dimensions. I think I have another chapter 3 problem in here. Let's do 3 dimensions. Just flip it over. Okay. What do you think the trick to this problem is going to be? Position vectors that turn into unit vectors, right? So being able to find unit vectors is going to be really important in 3 dimensions. So the question asks us, determine the tension developed in cables AB and AC and the force developed along strut AD for equilibrium of the 400-pound crate. So they're telling us right here we've got 400 pounds. Okay. So this is an equilibrium problem of a particle, so it has no size. So if we were to draw our free body diagram, we'll have 400 down. We'll have some TAB. We'll have some TAC. And we could draw TAD as tension if we wanted. You can see right away that it's compression, so I'm just going to go ahead and draw it that way. Some TDA like so. So we have 1, 2, 3 vectors that are unknown. So that means we really have 3 magnitudes that are unknown and 3 directions that are unknown. So there's 6 unknowns. Right? How many equations can we write in 3 dimensions for equilibrium of a particle? 3. Right? Some of the forces in the x, the y, and the z. So we need to go about determining from the problem the direction of these guys, okay, so that we can get down to our 3 unknowns. So what I'd like you to do is I want you to find for me the unit vector for DA, AB, and AC. All right? So we'll pause. I'll let you find the unit vector, and then we'll get back together. Everyone get some unit vectors, hopefully like this. Okay, so I found the position vectors, found their magnitude, and then the unit vector then is just the position vector divided by the magnitude. So it's negative 2 over 6.5 minus 6 over 6.5 plus 1.5 over 6.5 for AB. Okay. So then, yeah, Michael.
Question, I think I forgot something. So is it, for negative or positive, is it from B to A or is it from A to B?
Great question. So is it negative or positive from B to A or A to B? I try and write my subscripts in the direction the vector I'm drawing the vector. So in this case, I've drawn T is going from A to B, so it's TAB. And so I think, how do I go from A to B? And I'd have to go negative 6 in the Y, negative 2 in the X, and positive 1.5 in the J. But then if you look, notice at DA, we're drawing it as going from D to A, and so then it's 0, positive 6, positive 2.5. All right?
Thank you.
Yeah, no problem. That's exactly why we're doing this. Okay? All right, so now I'll pause again, and I want you to write the 3 equations of equilibrium, because now we know the directions. Since forces are vectors, they're directed along these lines. We know that. So I now just have the magnitudes of these as the unknown. I have their directions. Okay, so go ahead and write the 3 equations of equilibrium for this, and then we'll check back. So hopefully you got some equations of equilibrium that look like this. Good check is to go down the columns and make sure, is this the TAB unit vector? Negative 2 over 6.5, negative 6, 1.5, negative 2, negative 6, 1.5. And then for AC, 2 sevenths, 6 sevenths, 3 sevenths, 2 sevenths, 6 sevenths, 3 sevenths. And then for DA, 0, 6, and 2.5. And then you can't forget that you have that load in there, right? Lots of times that's a very common mistake students make on exams, is that they'll do all this work really well and they'll get down to here and then there will be no load and they'll say, it says false on my calculator. Nuts!
Can you explain again why DA is not negative but positive?
Right here?
No, up.
Right here?
Yes.
Right here. Yeah, because when I'm, so why, the question is, why is DA positive instead of negative? It's because I'm starting at D and I'm going to A. Okay, so if I start at D and I go to A, I go in the positive Y direction 6. And I go positive Z direction 2.5.
Because also done A to D.
If I did A to D, then I would have to, these would be negative.
Well, other than the sign change,
Yeah. But the way I've, and it comes back to right here. In my free body diagram, I draw it as going that direction, right? And so then I have to say, okay, then it starts at D and goes towards A. If I'd drawn it in tension, which would be fine, if I drew it this way, the signs would be opposite. Okay? But I chose to say it's that way. Okay? Good question. Anybody get a chance to put this in a solver? What'd you get, Michael?
For tension AB, I got 386. Tension AC, I got 416. And AD, I got 770.
I got like 273.
Yeah, I got 273.
294, and 547.
Uh-oh.
Thought I put something wrong.
Yeah.
Okay.
Positive and negative 547.
Positive.
So what are the values people have gotten for TAB? 274. 295. 547. And those would all be pounds. Okay. Did you find it, Michael? Did you find where?
Not yet.
You got negative for?
For TAD.
Yeah, did you do negatives here?
Yes.
That's
Yeah.
why.
Oh, yeah, because I have positive.
Yep.
Okay.
So Travis was getting a negative 547, and he was figuring that out. It's because he did T8, or he did R8 D instead of RDA. So he had negative 6 over 6.5, negative 2.5 over 6.5, which just reverse the sign in this case. Okay? So you just have to make sure, Natasha, probably a more clear answer of why is it that way? It's because of my free body diagram. Make sure that the way you draw your free body diagram is the way you find your position in unit vectors. Okay, so if I draw AB going up and to the left, then I need to make sure that I find my unit vector going up and to the left. If I draw an AB in compression pushing down, then I would have to make sure that my unit vector went from B to A, was going down and to the right. So everyone thumbs up on that concept, right? Make sure the free body diagram matches how you find your position vectors. All right? Yeah.
Now on the test, could we do it the, I guess more recent way of the 6 equations?
Oh, good question. So Brendan's asking on the test, could we do this the more recent way with 6 equations? The answer is no.
Why?
Because what we're asking for here is the tension in these cables,
Right.
right? Well, I guess, how would you do that?
I don't know.
Yeah, right? Okay. How, I don't know is a good answer. So I guess you could try and sum the moments about each of the axes.
Okay.
It'd be a super long, painful way to do it, so it would not be the right way to do it. Okay? Because remember, a good engineer is a highly motivated, lazy person. Okay? And so you need to look for the path of least resistance. Okay? And in this case, it's noting that, hey, I need to find the tension in these. This point has to be in equilibrium. If you chose to do it as like a rigid body thing, then you'd still have to do all this work. Then you'd have to write moment equations, and you'd have to break each of these. You'd have some like, right, at each one of these, you'd have a by, this would be y, this would be bz, this would be bx, right? And then sum the moments and solve for each of those, but then you'd only get part of them, so then you'd have to multiply them by the unit vector to get the actual tension. It'd be wicked convoluted. Yeah, so the answer is yeah, maybe, but your odds of getting it right are much lower than doing it this way.
So would you find the moments when it could ask you to find like the components of the forces at like the joint D or the socket D?
Nope, because so the question is, if you needed to find the components of the forces at D, you wouldn't do the sum of the moments or anything, because you already know if this is a socket joint, you know TAD, right? So you know it's in compression, and the resultant is 547 pounds. So you just have to multiply 547, right, times the unit vector. And then we would know that there's some along this axis and some along that axis and none in the y, right? So if I took 547 and multiplied it by the unit vector, I'd get the reaction at D. Right? So let's just do that. If I want to find the reactions at D, I could say, well, it's 547 times this unit vector, 0I plus 6 over 6.5 J plus 2.5 over 6.5 K, and 547 times 6 divided by 6.5. 504.9, so really 505, but and then 547 times 2.5 over 6.5.
210.4.
Okay. So these are the reactions at D. So what we could find, right, is that D sub Y is 505, and D sub Z is 210. Okay. Everybody good? All right, let's see. Got time for one more. Looks like. I think that gets us out of chapter 3 for our review. So we've done our vectors in a bunch of different directions. We've done static equilibrium of a particle. And then we come to this concept of moments. Okay? So let's look at I didn't put a very simple moment problem in here. I kind of jumped straight to this tricky moment problem. Okay, 438 here, it's the door. Was this a graded problem maybe, or? It was an example problem? Okay. You guys remember how to do this? Okay, there's two different ways to do this problem. So let's talk about both of them. Okay. So the first thing we're asked, I think we did a different one. We did around a specified axis, find the moment, instead of finding the entire moment. So determine the moment of the force F about the door hinge at A. So here's A. Express the result as a Cartesian vector. All right? So let's do the cross product method first. Does anybody remember when we're finding the moment about something? So let's say the moment about A. What cross product are we interested in? R cross F, right? R cross F, where R is the position vector from A to where? To the tail of the force, or to the line of action of the force? Remember, this is the cool thing about the cross product method, is that this position vector is the position vector from the point we're summing the moment about to any point along the line of action of the force. So remember, in 2 dimensions, if we have point A here and we have a force F that's up here, I need to find, if I want to find the moment, I take the line of action, and the distance I need to use is this perpendicular distance here, right? It is not that distance.
Can you say that one more time because of the picture?
Okay, so the moment here is F times D, not F times R, when you're just doing scalar moment analysis. It's always the perpendicular distance. Okay, so when we're doing a scalar analysis, if we're looking for the moment about point A, we have to find the perpendicular distance between the line of action of the force and the point A. We have to. It's always the perpendicular distance. When we switch and we do the cross product, it becomes R cross F, where R is any position vector from the point we're interested in, A, to the line of action of the force. So it could be this R1 here. It could be some R2 that comes down to here. As long as it goes to the line of action of the force, it doesn't matter. And this is one of those magic of cross products, right? Because we all know cross products do funky things with perpendicularity, right? When you take the cross product of 2 vectors, what do you get? A third vector that's perpendicular to the plane that's created by the other 2 vectors, right? In vector math, okay? In engineering, we don't really care about that, right? We just care about the magic that happens that says, hey, when I cross the force with the position, I will get essentially that lever arm length that's perpendicular to them, okay? So in this case, there are 2 vectors I could choose to find my moment about A. I could choose a position vector that's AC. Technically, I suppose there's an infinite number, but there's 2 that are obvious choices. So RAC I could figure out, or RAD, right? And most of you, which is fine, would see, hey, the force is up here, and you'd use RAC, right? Because you see the force is up here, and you forget that it's the line of action of the force. And going RAD makes it a whole lot easier. Why?
Same thing.
There's only two, right? There's only two values in it. There's a 0 in one of them. So let's use RAD. Maybe we'll do both, right? And see if Andy can do 2 cross products in a row and get the same answer. That's going to be a challenge in and of itself, right? So RAD looks like it's from A to D. So I have to go in the positive x direction 1.5, in the I hat direction, and in the y direction it looks like I go 3. So 3 j hat and 0 in the k hat direction. Okay. Now I don't need to find the unit vector because the unit vector just has a magnitude of 1. So multiplying it by the force would not give me the actual lever arm, right? So I want the lever arm, so I'm leaving it as its position vector. And I need to multiply it by the force vector of 80 pounds. Unfortunately, I can't just do the 80 pounds, can I? Because that just gives me the magnitude. It's not really an actual vector. So I have to figure out what the vector of the 80 pounds is. So here I'm going to have to use a unit vector. So let's find RC to D. So to go from C to D in the x direction, it looks like I'm going -5 I hat. I'm going positive, oh man, it is some funky number, right? I'm going positive 3 plus the 4 cosine 45. Right? Can everyone see that? Because it's this distance here, which this is 4 right here. So could someone tell me what the 4 cosine 45 is? 2 point what? 2.82. All right, so that means that it's in the y direction. I'm going positive 5.82 in the j hat. And then in the k hat direction, I'm going down, it looks like, from C to D, and I'm going to go down 2.82, right, because it'd be the sine of 4, so minus 2.82 k hat. All right, we all together, everybody happy with where we're at?
What was the function you used to get the j hat again?
Well, it's just, I'm just finding distances, right? So I know the length of the door, or whatever this is 4 feet, and it's at a 45-degree angle, so that means in the y direction you go 2.82, and then I add that to the 3. Okay? But I can't leave it this way. I need to find the unit vector. So at this point, I would just stick that in my calculator and say, give me the unit vector of CD. Right? Everybody remember how to do that? Calculator has a unit vector function on it. Yep. All right. Sounds like some people are confused on that. So go catalog and then type the letter U and you just go down 1 to unit V. If you have an 89, you hit enter. And then I'll do -5, comma 5.82, comma -2.82, close parentheses. Too many arguments? Shoot, it makes me put it in rectangle, huh? So I have to do the square bracket so that it knows it's a vector. -5, comma 5.82, comma -2.82. Close the square bracket, close the paren, hit enter, and I get my unit vector. So then I see -0.611, or 12, I guess, actually. I hat plus 0.712 j hat minus 0.344 k hat. Or I can just multiply that answer by 80 right? Because that's what I'm actually looking for is the force vector. And find that the force from C to D, which has a magnitude of 80, has components of negative 48.9 in the I hat direction, plus 57.0 in the J hat direction, minus 27.5 in the K hat direction. Okay. Everybody see that? Like greasy fingerprints all over my calculator. Okay. So now, back to our regularly scheduled programming. We're looking for the moment about A, which we've said is going to be RAD, right? Crossed with the force vector FCD. Okay? We could do this by hand, or we could go back to our calculator, right? And do the same thing, catalog, then put in C, and scroll down till it says cross product. There it is. And take the cross product, and you do square bracket, the first vector, which is RAD, so 1.5, comma 3, comma 0. Close the square bracket, then comma, open a square bracket for the next vector, which is the force. I wonder if it will let me just go up here and hit enter. Ooh, it will. Look at that. Okay. And I get something like negative 82.8 in the I hat direction, plus 41.4 in the J hat direction, plus 232 in the K hat direction. Okay. Now, I could also do the moment about A using RCD. No, I couldn't. I need the other one. My other option was RAC, right? So RAC looks like in the X direction is positive 5. In the Y direction is negative 2.82 J. And in the K direction is positive 2.82. Okay, so let's see if we get the same thing if we do RAC crossed with FCD. So do the cross product again, and I'm going to do the open bracket. We have 5, comma, negative 2.82, comma, 2.82. Close the bracket, parentheses, and I'm going to go back up and get my force vector. Oopsie daisy. Uh-oh. I did something wrong. Told you it was going to be a challenge for Andy to get 2 cross products right in a row. Right? So what do we have? AC. That's 5. Ah, it's not 5, right? It's, no, right here the I would be 5 plus 1.5. This should be 6.5. Right? Well, let's find out if that's it. Yes, that was it. I just had that wrong, and this gives me the same answer. Negative 82.8 in the I hat, 41.4 in the J hat, and 232 in the K hat. Okay. Yeah, Michael.
I don't know how to do the
Cross product?
Yeah, on my calculator. So what are you doing exactly?
Sure.
Just so I can.
Yeah, so if you can't do the cross product in your calculator, which they're going to show you how to do after class, because you're going to want to know how to do that, okay? When you take the cross product, so say we're going to do this cross product here, I would have 6.5, negative 2.82, and 2.
It's the one where you just put the 6.
And you do the diagonals, right? Okay, and then I'm going to cross that with my force vector, 48.9, 57, and 27.5, right? And this is I, J, K, right? So the first way I'd go diagonal down and to the right. So I'd have 27.5 times negative 2.82 I hat plus 2.82 times 48.9 J hat plus 6.5 times 557 K hat, right? So I just did diagonals down and to the right. And then I come back and I'd say minus I going the other direction, 2.82 times 57 I hat minus 6.5 times 27.5 J hat minus negative 2.82 times 48.9 K hat. And then you combine like terms and get the same answer. Does that make sense? But this is a lot of laundry, right? Compared to just sticking it in your calculator correctly. All right? Okay, we will continue this on Wednesday. If looking at the packet you don't see something that you want to have reviewed, please email me before Wednesday so I can pick out a few problems for that. All right? Yeah, Natasha.
I have a small suggestion.
Yeah.
About the final.
About the what?
The final.
About the final. I love suggestions about the final.
No, you said we're gonna have 6 different problems, right?
Maybe.
Why not make it 7 and we can choose 6?
I might. Sometimes I do that. Yeah, sometimes I will do that where I give you. It's really interesting actually. Sometimes I'll give you 7 and you choose 6. And sometimes students love that and sometimes students hate that because they don't want to have to spend any time choosing which ones they want to do. Which to me, I would love it because I'm like, oh, I don't know how to do that one or it's going to take me forever, so I'm not doing that and move on. But some students hate that.
It's
So
just like some people are better at certain.
yeah. Yeah, I'll think about it. Yes, the final is Monday.
Regular time?
Regular time. Okay?